as apologies because I'm going to go for English. My name is Mena Duran. I'm doing a PhD in green chemistry in the University of York. And I'm working with STARBONS, that they are a material made in the University of York around 2006. So I'm doing esterifications, I'm doing catalysis with these materials. So in the outline of my presentation, I'm going to talk about a short introduction about what are the STARBONS, I'm using microwave chemistry to do my reactions. I'm going to talk about the experimental setup that I used, the main results that I have obtained, and finally a conclusion. So these black stuff that you see there are my magic powders that are the STARBONS. What are the STARBONS? The STARBONS arose like an alternative for preparing carbonaceous materials, but mesoporous carbonaceous materials. Usually, they were made using templates, but using templates generates more and more residues and waste. So since a point of view of green chemistry, you try to avoid the generation of toxic waste or using less energy. So the STARBONS were discovered by Vitaly Budarin, is a researcher in York, and what he found is that we need to have like an expansion of the starch. STARBONS are starch, and the name comes from that. Starch, star, and carbon, bond, so STARBON. So in the, I don't know. Here. So there are several steps to achieve the formation of the STARBONS. The process consists first in the gelatinization of the material. You have powder, flour, you do that gelatinization in water, which allows to open the structure. So after that, what you do is a retrogradation. The retrogradation is a cooling at 5 degrees C around, and you leave it like for 2 days. What makes that is that you prepare a structure, so you make it more stable. But as I said in the beginning, the first step, you use water. So the following step is the interchange. Oh, sorry, we don't have it here. So you do an interchange. So we use water, and now we are going to use a solvent, in this case, ethanol. So that permits the stability of the materials. And the following step is the drying. So you are going to, you have the starch, you open, you try to maintain the structure with the retrogradation, and after you are going to dry. What we want to do with this, with the retrogradation, is maintain the open structure of the starch. And the final step is the pyrolysis of the material. So you prepare the material, you got a powder, but now we are going to do the functionalization through the pyrolysis. So again, what are the STARBONS? Here, what I want to show, do we have light or something to show? No, I don't think so. No, okay. Well, this is a graph that I want to focus here. Functionality and temperature. What I would like to show here Okay, so in this graph, what I want to show is functionality in the horizontal and temperature in the vertical. What we have with the STARBONS, one of the points of the STARBONS, of making the STARBONS, is that we can play around functionality depending on the temperature of carbonization. So if we work in low temperatures, we have more of the sugars, the structure of the starch. But as we increase the temperature, we can see that we have the graphitic-like of the material. So this is going to be key in the uses of the materials. So, as I said, functionality depending on the temperature of carbonization. About microwave chemistry, I think, well, I'm not sure if you are related, but it has been arose like a new approach to do synthesis in organic chemistry, trying to get higher yields, trying to get high selectivity, using less energy, because taking in account the fact that with a microwave, we disperse the energy in the medium instead of heating first the device and after doing the transference of heat. So taking that in account about my materials and about what I'm doing, and I want to present my main objectives in this research. It is quite wide because I'm trying to say I would like to understand the chemistry of the STARBONS. The STARBONS are new materials. They have different functionalities depending on the temperature, but how they work, why they do a reaction or why they don't do a reaction, I need to correlate that with the properties of the materials and the results of the reactions. And as I'm using microwave chemistry, I also would like to know what are the best conditions to carry out the reactions. So, the experimental part. Another thing that I would like to point in this presentation is STARBONS now are a company. They started in 2006 when they discovered it, but now it's produced a larger scale. They have STARBONS Limited that is started in 2011. So one of the things is try to do this a larger scale. So here what I am showing you is the production of the STARBONS. I have 3 starting materials, 300 degrees C, like 10 kilos each, 400 degrees C, and 800. And I show you in the graph that I would like to have. I have different functionalities depending on the temperature of carbonization. So what I did is from 300, I create 350, and from 400, I create a range of STARBON carbonization at different temperatures. The carbonization was done in oven, 10 degrees C per minute at the first rate, and after 1 degree C per minute, and hold for just 1 hour. But the STARBONS by themselves, they are not catalytic active. So I needed to put a little bit of another function to make them active. So I did a sulfonation of the STARBONS. As I said, we tried to do this at a larger scale. We did it like to 80 to 90 grams. That is considered larger scale because at the beginning it was done just with 1 gram, 2 grams. And I did a sulfonation at 90 degrees C for 6 hours, and after several washes to try to remove the excess of sulfuric acid, and after I dried the materials to be tested. So, as I said, I want to know how the STARBONS work, why they perform as they perform. So I needed to choose reactions. In this talk, I'm going to talk just about the microwave reaction of levulinic acid, lauric acid, and using methanol. The normal conditions of these reactions were carried out at 30 minutes in the microwave, and the ratio was 5 millimoles of the acid and 3 milliliters of the alcohol. Well, I have a question for you to see that if you are paying attention. What do you think that is better? I did the reactions, I did it by conventional heating because I needed to have the reference. And I also do it that by microwave. Which one do you think that was the best? Voting? Microwave people? People that love microwaves? Yeah, microwaves. Yeah, I did the reactions and I got the microwave in 30 minutes, and this is the perform in the conventional for 12 hours. So in this is the esterification of lauric acid with methanol. And also here, what I want to show is, this is a STARBONS 300. If you can remember the graph, I said I'm working with two extremes. 300 degrees C, that is like, it has a combination of hydroxyls and carbonyl groups, and the 800, that is a high temperature STARBON, that it has more graphitic-like structure. So I did this, and I got 88, almost 90% of conversion of the lauric acid to the ester in 30 minutes in the microwave. And with the 800, it was a little bit less, but it still was doing okay. In the case of levulinic acid, a small molecule, if we can compare lauric acid, that is a large hydrophobic carbon, we can see that the levulinic acid, more than 90% of conversion with the STARBONS 300. 800 still is less the conversion. But here I think, if we want to compare with a conventional heating, microwave results more efficient in this reaction. So here in this graph, what I want to show, because one of the questions, could you improve the reaction? Could you improve the conversion? Yeah, we try to do it with increasing the time. We go to 45 minutes, and we almost got 98% conversion. However, when we talk about microwaves, if we want to do microwave reactions, longer reactions, just close to 1 hour, sometimes it's not like good view from other researchers, no? Because usually reactions in microwave could be just 2 minutes, 5 minutes, 10 minutes, 15 minutes, but 1 hour, it will be not a good one. For this reason, we got 30 minutes like a medium. Well, as I said, what I want to do is check what happened with the STARBONS. So I have a range from 300 degrees C, that is the STARBON made, to 800. And what I found here is like low temperature STARBONS, 300, 350, perform better than in the middle 550, 600 degrees C of the STARBONS. That's, as I said, it could be related with the structure. We are going to see that later. And this STARBON 800, it looks like a curve. So low temperature, very good, high conversion. In the middle, not as good as the beginners, but at the end, again, we can like try to recover of the conversion. But one of the things here, when we talk about catalysts, and we reuse the catalyst, how long can you use the catalyst? So I did that screening for the esterification of lauric acid. I'm doing with the STARBONS 300. Here, at the beginning, I was just trying to remove the catalyst, drying, and try to reuse it. After a second, third use, my run was very low. So this could be because the excess of lauric acid that didn't react stays in the surface of the material. So I would say, okay, we can wash it. And I found out acetone is a good solvent for removing the excess of lauric acid. So I washed with acetone, and I went back to the efficiency of the conversion, no? The higher conversion. So it's still, I can say, 7 times you can use it, and it's relative, okay? But what happened when I use a STARBON 800? This is the high temperature STARBON. That is the graphitic-like STARBON. What happened? After 3 uses, it done, and I washed it with acetone, trying to get it back, and it didn't work. So second 2 times, and the third time, STARBON 800, it looks like it's not stable to keep going with the reactions. In the case of levulinic acid, I did the same screening, STARBONS. If you see, it's like the same behavior. Low temperature, 300, 350, looks okay. In the middle, again, I have that down of the conversion, and again, 800, try to recover and see, okay, I can do more conversion. Well, one other point of view that we can try to see, we are using 20 milligrams of catalyst and 5 millimoles of acid. That is less than 1%. So I increased the quantity of catalyst up to 40 milligrams. Now, these that were low, I try to reach 85, 90% of conversion. But still, it looks like the low temperature STARBONS are better. And if we want to try to reduce, what I want to show here is, again, 300, 350, that their low temperature STARBONS behaves more stable than the others, that is STARBONS 800 and 550. So now the question is, what makes the reaction happen? What is doing the reaction? It is that surface area. We measure the surface area here. Is the pore diameter? Is the mesoporous material that we are claiming that we have? Or is the sulfur content in the materials? As I said, I did a sulfonation. And here what I want to show you is, this is the behavior, no? Low temperature STARBONS behave very good, than high temperature STARBONS or the middle. But here in the surface area, we can see that there is not like a correlation. High surface area gives high conversion. So here, what I found is the percentage of sulfur that was carried out by elemental analysis. It looks to be key in the performance of the STARBONS. So, as I said, what I'm trying to claim in this presentation is, well, the functionality. Low temperature STARBONS 300 are more hydroxyl amylose carbonyl than the 800 that we have more graphitic-like. So functionality is key here for the performance of the STARBONS. So in conclusion, what I have, I think that I can claim that I discovered a methodology that is to prepare sulfonated STARBONS. They can be used for several times. In the case of high conversions, we observed that with a low temperature STARBONS, that it was 300 and 350. STARBON 800, it looks like it's not very stable, but this conversion could be related not just with the surface area characteristics, but with the percentage of sulfur in the materials. So I would like to thank my supervisor, Dr. Duncan Macquarie, Mario De Bruyne, Vitaly Budarin, Helen Parker, that helped with some analysis, my sponsor, CONACYT Mexico, and also the Secretary of Education in Mexico. So thank you for your attention. If you have any questions, happy to do.